Thank you very much. So, my name is Juraj Kabzan. I'm a master's student at the ETH Zurich studying robotics. And I would like to present to you on behalf of AMC Driverless, our project, how we used ROS in our autonomous race car, which was built for Formula Student Driverless competition, the first ever competition. At the beginning, I would like to start with a short video that you get a feeling about the car, how they look like, or what you can achieve with ROS in very short time. Okay. There should be music, however, apparently doesn't work. So the car is a single-seated car with very high volt torque, which can achieve very fast accelerations. However, the top speed is very limited since the track is very tight. The car is still interchangeable, so in the sense of still a driver can drive it, and we turn on autonomous mode just by switching a switch. It's fine, it's fine. Yeah, sure. So in this presentation, I would like to tell you shortly about our team.
Is there any more audio?
No. The competition by itself, algorithms used, an overall concept of the car, and the tools we have developed during the entire project. So the AMC Racing was started in the 2007 as a combustion car, but we changed immediately to the electric cars as they were announced. We were first in a world ranking in an electric competition for multiple years, 2013, 14, 15, and hopefully we will be also this year, 2017. And AMC Racing holds a world record in acceleration of electric vehicles from 0 to 100 with time something a little bit above 1.5 seconds. The new driverless team this year consists of 8 master students, and we were helped with additional 8 other guys who helped mainly with the hardware part of the car. At the beginning of the project, we set 3 main goals. Since it was first competition ever, we wanted to finish all dynamic disciplines. We wanted to maximize overall points, thus win the competition, and pass on the knowledge to the team, to the next year team, 2018. Shortly about the competition itself. So Formula Student Germany is a huge design competition for university students where every team should build a single-seated Formula-style race car which is driven either electrically or it has a combustion engine. And this year, as the first time, there was driverless category where every team should rebuild old car and change it to their autonomous versions. On this picture, you can see 115 teams from around the globe, where 65 are combustion, 35 are electric, and 15 are autonomous. So the FS Formula Student Germany competition is divided into 2 parts, static disciplines and dynamic disciplines. I will mainly focus on the dynamic disciplines, which are skid pad and acceleration, and the main event, which is a track drive with efficiency. As you can see, it contributes the most to the final points. The track drive, in track drive discipline, every team drives on a previously unknown track, which is marked just by cones on left and right side, yellow and blue, as you can see on the picture. Every team should start, drive 10 laps, and finish autonomously. Everything must be done just by turning on the switch. Since the track is unknown, there is possibility to do so-called track walk, so 30 minutes before the actual drive. Every team has possibility to somehow push around a device with a single wheel and any kind of sensors on top of it and build either map or do whatever every team wants. The second dynamic discipline is skid pad, where every team should drive 2 circles to the right and 2 circles to the back, start and begin autonomously. In this discipline, the map is previously known, so we know precisely the position of every cone and how it will be oriented. thus it should, so the finishing, this is sped up, but it should look like something like this, so start and finish totally autonomously. The used platform for this project was a Fluela, which was built for Formula Student Electric competition in 2015. It is a four-wheel driven electric car, which gives us the possibility to use torque vectoring, so we are able to control every single wheel independently. And we decided to just brake by recuperation, so not use the real brakes during the drive, just for the emergency. It has, as you can see on the rendering, it has full aerodynamic package, high wheel torque, which allows it to accelerate from 0 to 100 just under 2 seconds. And it has very lightweight design, thus everything is constructed from carbon fiber. In order to make it drive autonomously, we had to add some multiple sensors. So the first one is a ground speed sensor, which measures the lateral longitudinal velocities in the body frame of the car. This sensor was used also in the year 2015, so we added more. First one is a stereo camera with the IMU on top of the main roll hoop. INS, so GPS and IMU under the seat, and in the front, the LiDAR, Velodyne sensor. Now I will shortly tell you about the overall concept and algorithm used, which were based on the framework See, Think, and Act. So at the end, we had an electronic control unit, which was a real-time computer, which was handling all the steering, motor, and EBS, so emergency brake system on the car, which was communicating with a master computer, which is industrial-based computer, which was running already ROS, which was communicating, gathering all the data from available sensors as LiDAR, odometry, GPS, or ground speed sensors, was running the LiDAR pipeline, so detecting the cones in the point cloud, building a map, so running a SLAM and forwarding all the position in the map to the sensor fusion. And in the end, a trajectory generation, so figuring out where to go, where the truck actually is, and controlling to follow given path. In addition, we had to equip the car with one additional computer, which is a slave computer, also running ROS, is the high-end i7 computer, which is running just the visual part of all algorithms, so gathering the stereo camera and IMU, and running SLAM and cone detection. Everything is equipped in a side pod, as you can see the gray small box over there with many heat sinks on top. There is all the computers are packed in there. Since this project needed many packages to be run at the same time, we have developed so-called high-level safety package, which was launching all the required nodes and monitoring the used resources of every of these nodes. Every package was streaming heartbeats and giving kind of health. And the high-level safety was listening to all of these, and it has measured how much of every of these package can miss, how many heartbeats can be missed. And if multiple of these heartbeats are missed, the high-level safety can trigger emergency brake system and lock all the wheels and stop the car as soon as it's possible. Of course, we have developed some kind of configuration file, YAML file, where we can specify what packages should be launched at the same time for a given mission, what topic are for the heartbeats, and what should happen if multiple of these heartbeats are missed. Of course, we had to run it somehow, so we have developed a control station based on the RQT plugins, so it's totally configurable, which launches the given emission, the given event, and we are able to locate or see there perfectly what nodes are using what kind of resources. And at the same time, it starts to record, so start to record all the ROSBACs, which further on we can handle. On the right side, you can see another GUI where we can filter efficiently the packages we want to use or just the messages we want, for example, or just the sensors without any kind of debugging in the future. Now, a little bit on the algorithms by itself. So the slave, which is running the visual pipeline, it has the stereo camera with INS, as I said already. And there we used Rovio, which is a visual odometry with fusion with the ORB SLAM, which is a visual SLAM. And Rovio is some kind of prior for the visual SLAM. As you can see on the video, we are able, with this system, to build the map and successfully do also the loop closures. And this happens while this data set was driven by a human driver, so it's kind of fast. On top of this, we run the cone detection, which is based on the cascade classifier on these features in the map. This is open source project, and there is also one of our data sets, the one that you see on the video, so you can download it, play with it. In the master side, we had the semantic SLAM, which is based on the fast SLAM, so it's particle-based SLAM. For this purpose, we have developed two main packages. So the first one, which was simulator, configurator, and observer. That means that we are able to simulate the cone observations and change any kind of parameter in the SLAM. And at the same time, it's kind of useful for visualizing. And the SLAM localization mode runs on the car. The SLAM can run on two different modes. So either we can be mapping, so run actually the SLAM, or we can just localize already in preloaded map. It is very useful to develop GUI tools or graphical user interface because it speeds up all the development. You can see the simulator here where we can draw any kind of track we want, any kind of cone positions, and it simulates the observations a given radius. In this case, we don't care about left and right side, which is just without the information from the cameras. On the right video, you could see the gray part, which were the potential particles, and this is the most likely particle, and when the loop closure happens, we can draw left and right boundaries and complete the middle line automatically. Next, for the sensor fusion, we use the extended Kalman filter, which fuses all the information from sensors. So if position in the map is available, so after the loop closure, it is also fused there. Otherwise, we use just IMU velocity sensor wheel odometry. Of course, the sensors are not perfect, so we have introduced also outlier rejection, and the output of this extended Kalman filter is the full state of the car. As you might know, it's sometimes hard to debug the Kalman filter. Thus, we used many custom debugging messages which were used just purely for debugging and further on visualized in RQT multiplot. It's a very useful tool. And also RVs, of course, with many plugins as IMU variance plotting. We had also we developed also Gazebo Simulation, which was able to simulate the entire car and was able to simulate all the sensors which we have on the car. The car can drive in two different modes. So the first, which is we call discovery mode, where there is no or very little prior knowledge about the track by itself. So we drive just based on the local observation of the cones. Thus, it's very slow because it has to assume there comes any kind of hairpin very close. So let's say 180-degree turn, very sharp turn. However, while during this discovery mode we are mapping, and if the map is built, so loop closure occurs, we can automatically switch in a race mode, which assumes, of course, the map is always available. This race mode is based on model predictive control, which takes into account the dynamic vehicle model, all the constraints, boundaries. We are able to solve this online with the Forces Pro solver, and we run it approximately at 20 Hertz. The result you can see here. So at the beginning, we write just in discovery mode based on the local observation of the cones, where we find the most likely track, where the track actually goes. By the moment where the switch happens, we can switch to the race mode, drive with the model predictive control, and drive way faster. This around 50 or 60 kilometers an hour, and the track is very, very tight, around 3.5, even less meters wide. The next discipline is a skid pad. As I said, we should drive twice to the right and twice to the left. We know already the map, so the SLAM is not happening. We are just localizing in a predefined map. And the control in this event tries to maximize the lateral tire force through slip angle feedback control. When we assume that we compare this control with a human driver, with a similar car, with the same temperature of the tires, we have achieved faster, we are faster with this autonomous system than a human driver. Oh, I want to show a video. And the result you can see here. There you see the GG plots, so the accelerations and the speed. This is in a somewhat, I guess it was 0.05 seconds faster than a human driver. And we achieved there from 1 to 2G lateral acceleration, what is kind of a lot. And stop autonomously. The last part, I would like to tell you something about software tools we used in the project. So we developed the Gazebo Simulation, of course, which simulates the entire car, all the sensors. And we used this extensively during the control developing. We used there all the plugins were used from normal repositories. So we just used the Gazebo plugins for sensor simulation. However, at some point for the control development, we needed some kind of more precisely know what are the dynamics of the car, which you might know the physics engine is, you can't really know it. So we changed the Gazebo physics engine with a Python script, which was simulating the car precisely with our tires, with perfectly we know the curve of the tires. At the beginning, when we submitted this talk, it was still before the race. But now we are already after the race, and we can say that we successfully achieved all our goals. So we won the competition, and we were the only car who was able to finish all the disciplines, especially the track drive. Thank you. At the end, I would like to tell you how we kept the entire team together, since we were 8 people who half a year were extensively writing code. We all used Ubuntu 14.04 with the ROS Indigo. All the code was stored in a Git repository, and we synced it over the Bitbucket. We used extensively simulations as much as we could, because many of our bugs were figured out in the simulation. And some kind of hint which we figured out during the project is that the visualizing is one of the most important things. So visualize really as much as possible. Also, lots of testing. We tested every week. We tested on most of the time on airports. You can see on the picture there's our ground unit where we spend a lot of time. Before every testing, we upload our code to the Bitbucket, which is automatically compiled on Jenkins. So we are sure that anything what goes on the car really compiles and works. So it was also testing nightly simulations. So we had some predefined things which the car should do, and if the car does it, then it can go really on the real car. Logging. It's very good to log as much as you can. However, it happened to us that at some point we were logging too much, too many topics, and the ROS bag record was the most pricey node to run, so it took almost all our computing performance. And at some point, half of our packages just froze, and the car just went totally out of the course. So take care, log a lot, but not too much. At the end, I would like to thank to all our sponsors, and I'm happy to answer any questions. I would like to also introduce 2 colleagues from our team. We came in 3, so Victor Reichwart and Hendrik Hubertus Hendricks.
We've got time for just we've got time for just one question. The first one at the microphone here.
Thank you so much. Very inspiring work. Really liked it. What's the rate of your sensors, and what's like your computational time when you finish up to the Actorics?
Oh yeah. Okay. So I can answer this question. Is it working? Yeah. I can talk here. It's better. Okay. Yeah. So for the LiDAR, we get 10 hertz data. And for the more like non-data intensive sensors, like the GPS and the IMU, we get them at 100 hertz. And the computational time it really depends on the package. So for the SLAM and stuff, it's about 100 milliseconds. And for the Kalman filter itself, it's about
few microseconds.
Yeah, few microseconds. That's really fast.
Okay, thank you so much.
Fantastic. Let's thank the team again. Thanks.
Oh.